So now we're going to have a look at complex roots of polynomials. Okay, and this is a sort of intersection of topics 1 and 2 in the IB course, algebra and functions. Okay, this has many elements of factor and remainder theorem and long division from functions, but of course it's also part of complex numbers in algebra. And it's more like one of the uses of complex numbers, okay, the reasons why we need to know about them, rather than just working with some of the harder parts of polar form of complex numbers and those kind of questions. So going back a little bit now, looking at quadratic roots, okay, you'll remember from the quadratic formula and discriminants that when the discriminant is positive, okay, you can use the quadratic formula and you'll find a positive inside the square root, so a positive discriminant, and you will get your two roots, okay, or two x-intercepts. Okay, so this one, you could say the graph would look something like this, okay, with roots at -1 and 5. Okay, real roots, real numbers there, 5 and -1. Okay, but then what you'll see in some quadratics is if you use the quadratic formula, minus b plus or minus the square root of b squared minus 4ac is 180 all over 2a, minus 12 over 6 is minus 2. This is going to be negative 36 over 6. And, well, negative 36, root of negative 36 is, you can see it as root 36 times root of -1, which is 6i. And 6i over 6 is I, so you'll have -2 plus or minus I. Okay, so -2 plus I is one of your roots, and -2 minus I is your other one. Okay, and well, you may have seen that before, depending on how much complex numbers you did before IB. But the graph of that quadratic may look something like that. Okay, you cannot see it sort of across the x-axis. Okay, it has no real roots, no visible roots, x-intercepts on the graph. It does still have two roots. Okay, every quadratic will have two roots. Okay, it's just that some of them will be complex, like these two here, and sometimes they are repeated roots as well. Okay, so well, you should know most of that already, but what we get to in HL is beyond the quadratics, any polynomial, to be honest. So let's see here. We have a cubic. Okay, you'll never be asked to factor a cubic from scratch. Okay, because it does require some guesswork or maybe some more advanced techniques. But you may be asked to do that kind of thing with a hint like this, with some other information really. If x equals 5 is a root, then x minus 5 is a linear factor. Okay, you'll know that from the factor theorem. Okay, so we can say that this is a linear times a quadratic. Okay, a linear times a quadratic will give us a cubic. Okay, that's fairly simple. And well, you could do the cubic divided by x minus 5 with some kind of long division or synthetic division. I prefer to go for more of a comparing coefficients route. Okay, I look at this and think x times ax squared needs to be 2x cubed. So what would a need to be? 2. Okay, minus 5 times c needs to be 15. So c needs to be minus 3. Then the final one will be a tiny bit trickier. You can either take the x squareds or the x's, and let's just go with the x's, because there's two combinations that will give us a result of minus 28x. C times x will combine with minus 5bx, and that should equal minus 28x eventually. C is actually minus 3 now. So we'll have minus 5bx equals minus 25x, and so b is 5. Okay, we have our quadratic. (2x squared plus 5x minus 3. And you can factor that one more time using whatever factoring method you like. But I can tell you that's just going to be plus 3 and minus 1 there. Okay, so roots, apart from 5, we have a half and minus 3. Okay, so a cubic will often just have 3 real roots. Okay, this one, for example, might look something like this, where this is minus 3, this is a half, and this is 5. Okay, so that still hasn't really got to complex numbers, so what about another one of these? Quick as possible, won't go through that whole process again, we'll get to the interesting part of it. Okay, we're told that instead of telling us the root, they told us a factor of this one, 2x plus 3. And actually, I can always see that this needs to be just a 1x squared. I can see that this needs to be a 5, okay, because 5 times 3 needs to equal 15. Okay, and x squared times 2x needed to equal 2x cubed, so that's all fine. Then 5 times 2x plus 3 times bx needs to equal 22x when it's all combined, when you combine your like terms. So b would 3 times bx needs to equal 12x, so b would need to be 4. Okay, again, you may prefer your synthetic or long division there. Now you might try to factor this, okay, to find the other roots, but you might be struggling, and well, that's because if we use the quadratic formula instead, minus b plus or minus square root of b squared minus 4ac is that over 2a, we're going to get this here, and yes, we have a complex number. We have a root of a negative. Okay, that's minus 2 plus or minus 2i over 2. So minus 2 plus or minus I. So those are our final two roots. And well, if we have a root at 5, we said x minus 5 was the linear factor. And the same thing is true here. So we have our 2x plus 3, and we have x minus 2 plus I, and x minus 2 minus I. Okay, and I could tidy that up a little bit. Okay, you got to be very careful with your double negatives here. Okay, and they're a little bit more awkward because there's 3 terms essentially inside these brackets here. But that is our factored form. Okay, those are our 3 factors, although the question actually said find the other roots, and that was already complete here. Okay, minus 2 plus I, minus 2 minus I. Okay, and a very important note here would be to say that these are complex conjugates of each other. So when you have your real part that stays the same in both numbers, and it's plus or minus the imaginary part. That's a complex conjugate, something you will have probably seen to help you divide complex numbers in Cartesian form. So, what if we go beyond cubics? We're not going to really do one properly from scratch, let's say, but a polynomial to the power of 4, a quartic, you might call it. Well, we saw that if a cubic can be factored into a linear times a quadratic, okay, a degree of 1 times a degree of 2 gives you a degree of 3. Well, two quadratics multiplied together would give you a degree of 4. Okay, degree of 2 times a degree of 2. And, well, that's what you get. Okay, you're going to get a quadratic times a quadratic. We know already that there are 2 or 3, however you want to think about it, possibilities for roots from quadratics. Okay, I'm just going to call the 2 equal roots. I'm just going to call that 2 roots for the sake of simplicity, even though you may call that 1 repeated root sometimes. Okay, so either you have 2 real roots from a quadratic, or you have 2 complex roots, 2 complex conjugates. Okay, and you get that from both quadratics. Okay, and what that means is from a quadratic, you have any one of those options. So you could have 2 real roots and 2 more real roots. Okay, that would be a quadratic, I don't know, that could look something like that. Or you could have a 2 complex and 2 real. That could look, well, you'd only see 2 x-intercepts on a graph. Some quadratics look a bit like that. It could also look like that as well. Or it could be upside down as well. Or both quadratics could give you complex roots. In that case, you have no visible x-intercepts on the graph, and so it just won't cross the x-axis. So it might look like that, for example. Okay, and that would just be if the discriminant, that would happen if the discriminant was negative in both of those quadratics. Okay, in that example though, if you had the 2 complex roots from each quadratic, you would have a pair of conjugates from both. Okay, so you could have 2 plus or minus I as 2 of your roots, and 3 plus or minus 5i as 2 more of your roots. Okay, when n equals 5, quickly, let's see what happens. Well, how do you make 5 through multiplication? You could have a degree of 2 times a degree of 2 times a degree of 1. That's a quadratic times a linear. Okay, again, from the quadratics, you could have 2 real or 2 complex, 2 real, 2 complex, but there's no complex roots to be had from a linear factor. Okay, that is impossible. As we saw in the cubic, these linear roots, these linear factors were always going to give us a real root. That was never in question. So this linear root here, linear factor, sorry, would provide us with 1 real root always. Okay, and then again, you could have a combination of any of these 2 options for the 2 quadratics. Okay, so it could just be 5 real roots. It could be 1 real root and 4 complex, or 3 real roots and 2 complex. Those would be our only options. Okay, so based on everything we had there and everything you would assume would happen if you just carried on that pattern for bigger and bigger polynomials, degree polynomials, we have the following sort of summary of rules that we can get from this. Well, firstly, one thing we'll say is that the degree of the polynomial, the highest power, is equal to the number of complex roots, okay, the number of roots in total. Okay, in the quadratic, we had 4 roots. Whatever combinations we picked, we have 4 roots. Here, we have 5 roots. In the cubic, we have 3 roots, okay? And this is 3 complex roots, okay? And that does not mean, even though I wrote complex here and treated real as if it was something different, remember that complex numbers include real numbers within them, okay? The real number 2 can be written as 2 plus 0i. So the number 2 is a complex number technically. Okay, so even if you select some reals from all those combinations we were talking about, some real roots, they still count as complex. So degree of the polynomial tells you how many complex roots you are going to have. If z, a complex number, is a root, then z star, that's the complex conjugate, as we've discussed, then the complex conjugate is also a root. Okay, so as we saw here, if minus 2 plus I is a root, minus 2 minus I must be a root. Okay, that's how the quadratic formula works. There's no way around it. Okay, you always have a pair of conjugates in your list of roots. In odd degree polynomials, you must have at least one real root. Okay, well, that comes from the rule above. Okay, if one complex number is a root and you're going to have a pair, you're going to have its complex conjugate as well. If there are an odd number of roots, okay, you can't fill that with only pairs. Okay, we saw this with the polynomial of degree 5. Okay, when we had our pairs, we were left with one real root at the end left over, and so that would always just have to be a real root on its own, or at least one real root. Okay, it could be combined with 2 more or 4 more in that situation, but at least one when the degree is odd. We saw that with cubics as well. Okay, so trying to make this too long, but let's do one more example, a sort of IB question. Bringing all those things together. If we have this quadratic here, and 2 of the roots are these complex numbers here, A, B, C, and D are real numbers, D is positive. What are the other roots? Okay, that is just directly going to be this rule here. If one complex number is a root of your polynomial, then its conjugate is as well. Therefore, C minus I is the conjugate of the first one, and 2 minus ID is the conjugate of the other one. So those would be our other 2 roots. Okay, find the value of C and D. Well, one thing we can say here is that this polynomial equals this x minus all of the roots, respectively, all multiplied together. That's a bit long-winded, yes, when you have 3 terms inside the bracket like that. Now, oh, sorry, I shouldn't have put x, I should put z. But now we can think about just how that would be expanded, and then, therefore, what A, B, C, and D would need to be. Sorry, just C and D. So if we multiplied these 2 brackets together, you'd have to do 9 combinations of things, but lots of them cancel out. And, well, you could try that yourself, but I will tell you that, and remember that I squared is minus 1 as well. That would be one of the most important things. You'll get this quadratic here, okay? where even though you have two terms in your final term of the quadratic. Okay, if you multiply together the third and fourth brackets of the initial product, then you would get that. Okay, now we can think about how these would expand to get your original polynomial. The z to the power 4 does not really help us because we can see here that we just got z squared times z squared, so that's nothing to do with c and d. What about z cubed? Z cubed needs to be minus 10, has a coefficient of minus 10 at the end. The z cubed terms come from z squared times minus 4z and z squared times minus 2z. So let's multiply those terms together. We have that plus this, and this apparently needs to equal minus 10z cubed. Okay, we can simplify this to just minus 4 plus minus 2c, and all we need to do is solve, and we'll get c equals 3. Okay, then if we know c equals 3, then you could probably go back up here and put in a 10, 3 squared plus 1. And that's helpful because you know that the constant terms multiplied together should be 50 at the end. Okay, we've got 10 times 4 plus d squared. 10 times 4 plus d squared should equal 50. Divide by 10, subtract 4. You should get plus or minus 1. Okay, whenever we have multiple answers like this, go back to the start of the question and think, is there some kind of thing in the context of the question that rules out one of them? Can I have a negative? Is it to do with length, anything like that? And actually, it's more simple than that. It just tells us d needs to be positive. So no, actually, d just equals 1. Okay, c equals 3, d equals 1, and we are done. Okay, and that is complex roots of polynomials.